गुड मॉर्निंग स्टूडेंट्स। ਅੱਜ ਅਸੀਂ ਕਰੰਟ ਦੇ ਮੈਗਨੈਟਿਕ ਇਫੈਕਟਸ ਬਾਰੇ ਹੋਰ ਪੜਨ ਜਾ ਰਹੇ ਹਾਂ। ਅੱਜ ਅਸੀਂ ਐम्पेयर्स सर्किटल लॉ ਅਤੇ ਉਸ ਦੀਆਂ ਐਪਲੀਕੇਸ਼ਨਸ ਬਾਰੇ ਪੜਾਂਗੇ। ਪਹਿਲਾਂ ਮੈਂ ਅੱਜ ਦੇ ਲੈਸਨ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਤੁਹਾਡੇ ਨਾਲ ਸ਼ੇਅਰ ਕਰਨਾ ਚਾਹੁੰਦੀ ਹਾਂ।
After the completion of this chapter, the students will be able to describe the Ampere's circuital law, deduce an expression for the magnetic field for a straight infinite current carrying wire using the Ampere's circuital law, discuss the applications of the Ampere's circuital law, describe the magnetic fields inside and outside of a toroid and a long solenoid.
1826 ਵਿੱਚ ਫਰਾਂਸ ਦੇ ਵਿਗਿਆਨੀ ਐਂਕਰ ਮੈਰੀ ਐਂਪੀਅਰ ਨੇ ਇੱਕ ਲੂਪ ਵਿੱਚੋਂ ਲੰਘ ਰਹੇ ਇਲੈਕਟ੍ਰਿਕ ਕਰੰਟ ਅਤੇ ਕਲੋਜ਼ਡ ਲੂਪ ਦੇ ਚਾਰੋਂ ਪਾਸੇ ਬਣੇ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਵਿੱਚ ਸੰਬੰਧ ਦੱਸਿਆ। 1861 ਵਿੱਚ ਸਕਾਟਿਸ਼ ਸਾਇੰਟਿਸਟ ਜੇਮਸ ਕਲਾਰਕ ਮੈਕਸਵੈਲ ਨੇ ਇਸ ਨੂੰ ਹਾਈਡਰੋਡਾਇਨਾਮਿਕਲੀ ਢੰਗ ਨਾਲ ਰੀਡਿਰਾਈਵ ਕੀਤਾ, ਜੋ ਕਿ ਇਲੈਕਟ੍ਰੋਮੈਗਨੈਟਿਜ਼ਮ ਦੀਆਂ ਫੇਮਸ ਇਕੁਏਸ਼ਨਸ ਦਾ ਆਧਾਰ ਹੈ। To understand Ampere's circuital law, let us consider an open surface with a boundary C, and the current I is passing through the surface. Let the boundary C be made of large number of small line elements, each of length dl. Consider a small element and for which the direction of dl is acting tangentially to its length dl. Let the value of the tangential component of the magnetic field at this element be Bt. Then Bt and dl are acting in the same direction. Therefore, the angle between them is 0. Then the product of Bt and dl for that element is equal to the dot product of B and dl. If the length dl is very small and products for all elements of closed boundary are added together, their sum is equal to the integral around the closed path or loop. Therefore, summation of B dot dl over all elements on a closed path is equal to the line integration of B around the closed path or loop whose boundary coincides with the closed path. According to Ampere's circuital law, line integration of B dot dl over a closed path is equal to mu naught times the total current I threading the closed path or loop. Here, mu naught is the absolute permeability of the space. According to Ampere's circuital law, the line integral of magnetic field induction B around a closed path in vacuum is equal to mu naught times the total current I threading the closed path. इस रिलेशन नाल एक साइन कन्वेंशन जुड़ी है, ਜਿਹੜੀ राइट हैंड रूल नाल समझी जा सकती है।
ਇਸ ਦੇ ਅਨੁਸਾਰ ਰਾਈਟ ਹੈਂਡ ਦੀਆਂ ਫਿੰਗਰਸ ਦੇ ਕਰਲ ਹੋਣ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਬਾਉਂਡਰੀ ਟਰੈਵਰਸ ਹੋਣ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਹੋਵੇ ਤਾਂ ਥੰਬ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਕਰੰਟ I ਪੋਜ਼ਿਟਿਵ ਮੰਨਿਆ ਜਾਂਦਾ ਹੈ।
As per the sign convention for the closed path, I1 is positive and I2 is negative. Then, according to Ampere's circuital law, line integral of B is equal to mu naught into I1 minus I2. A relation current enclosing closed path ਜਾਂ ਲੂਪ ਤੇ ਸਾਈਜ਼ ਅਤੇ ਸ਼ੇਪ ਤੇ ਡਿਪੈਂਡ ਨਹੀਂ ਕਰਦਾ। ਆਓ ਐਂਪੀਅਰਸ ਸਰਕਿਟਲ ਲਾਅ ਪ੍ਰੂਵ ਕਰੀਏ। ਕਈ ਐਪਲੀਕੇਸ਼ਨਸ ਲਈ ਐਂਪੀਅਰਸ ਸਰਕਿਟਲ ਲਾਅ ਦਾ ਸਿੰਪਲੀਫਾਈਡ ਵਰਜ਼ਨ ਹੀ ਐਪਲੀਕੇਬਲ ਹੁੰਦਾ ਹੈ। ਇਹੋ ਜਿਹੇ ਕੇਸਿਸ ਵਿੱਚ ਅਸੀਂ ਇੱਕ ਕਲੋਜ਼ਡ ਲੂਪ ਅਸਿਊਮ ਕਰ ਲੈਂਦੇ ਹਾਂ, ਜਿਹੜਾ ਐਂਪੀਰੀਅਨ ਲੂਪ ਕਹਾਉਂਦਾ ਹੈ, ਅਤੇ ਇਸ ਦੇ ਹਰ ਇੱਕ ਪੁਆਇੰਟ ਤੇ ਜਾਂ ਤਾਂ B ਲੂਪ ਤੇ ਟੈਂਜੈਂਸ਼ੀਅਲ ਹੁੰਦਾ ਹੈ ਅਤੇ ਨਾਨ ਜ਼ੀਰੋ ਕਨਸਟੈਂਟ ਹੁੰਦਾ ਹੈ, ਜਾਂ B ਲੂਪ ਤੇ ਨਾਰਮਲ ਹੁੰਦਾ ਹੈ, ਜਾਂ B ਵੈਨਿਸ਼ ਹੋ ਜਾਂਦਾ ਹੈ। When there is a system with symmetry, such as for a straight infinite current carrying wire, the Ampere's law enables an easy evaluation of the magnetic field in the same way as Gauss' law helps in determination of the electric field. Consider a long, thin, straight conductor XY. When current I is flowing in vertically upward direction, the magnetic field is produced. The magnetic field lines are concentric circles perpendicular to the plane with their center lying on the conductor. Let us fix a field point P at a distance r from the conductor. We know that the magnetic field induction B at a point due to a straight current carrying conductor is equal to mu naught I upon 2 pi r. Here, direction of B is along the tangent to the magnetic field line at that point. चलो एक एम्पीरियन लूप इमेजिन करते हैं, जेड़ा रेडियस r वाला एक क्लोज्ड सर्कुलर पाथ है ਅਤੇ ਇਸ ਦਾ ਸੈਂਟਰ ਇੱਕ ਸਟ੍ਰੇਟ ਕੰਡਕਟਰ ਉੱਤੇ ਹੈ। ਹੁਣ ਕਲੋਜ਼ਡ ਪਾਥ ਤੇ ਪੁਆਇੰਟ P ਤੇ ਲੈਂਥ dl ਦਾ ਇੱਕ ਛੋਟਾ ਜਿਹਾ ਐਲੀਮੈਂਟ ਕੰਸੀਡਰ ਕਰਦੇ ਹਾਂ। ਕਿਉਂਕਿ B ਅਤੇ dl ਇੱਕੋ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਹਨ, ਇਸ ਕਰਕੇ ਉਹਨਾਂ ਵਿਚਕਾਰ ਐਂਗਲ 0 ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਰੇਡੀਅਸ r ਦੇ ਸਰਕੂਲਰ ਕਲੋਜ਼ਡ ਪਾਥ ਦੁਆਲੇ B ਦਾ ਲਾਈਨ ਇੰਟੀਗਰਲ integration of B dl cos 0 degree ਜਾਂ B times the integration of dl over the closed loop ਦੇ ਬਰਾਬਰ ਹੋਵੇਗਾ। On substituting the value of B, that is B equal to mu naught I upon 2 pi r, line integral of B becomes equal to mu naught I upon 2 pi r into 2 pi r, that is mu naught times I. Let us continue our understanding of Ampere's circuital law for any arbitrary closed path. Now we consider any arbitrary closed path around a long straight conductor XY carrying current I from X to Y. Let us divide the closed path into a large number of small elements of length dl1, dl2, dl3 and so on. Let d theta 1, d theta 2, d theta 3 and so on be the angles subtended by the various small elements at point O through which the conductor is passing. The sum of all such angles should be 180 degree or 2 pi. If these small elements are small circular arcs of radii r1, r2, r3 and so on respectively, then d theta 1 is equal to dl1 upon r1, d theta 2 equal to dl2 upon r2, d theta 3 equal to dl3 upon r3 and so on. If B1, B2, B3 are the magnetic field induction along the small elements dl1, dl2, dl3 and so on, then B1 would be equal to mu naught upon 4 pi into 2I upon r1, B2 would be mu naught upon 4 pi into 2I upon r2, B3 would be mu naught upon 4 pi into 2I upon r3 and so on. In each case, the magnetic field induction B and current element vector dl are in same direction. Therefore, line integral of B around the arbitrary closed path is equal to the vector sum of B1 dot dl1 plus B2 dot dl2 plus B3 dot dl3 and so on, also equal to sum of B1 dl1 plus B2 dl2 plus B3 dl3 and so on. On substituting the values of B1, B2, B3 we get the line integral of B around the arbitrary closed path as equal to mu naught upon 4 pi into 2I upon R1 into dl1 plus mu naught upon 4 pi into 2I upon R2 into dl2 plus mu naught upon 4 pi into 2I upon R3 into dl3 and so on, or mu naught I upon 2 pi into dl1 by R1 plus dl2 by R2 plus dl3 by R3 and so on. On substituting the values of dl1 by R1, dl2 by R2, dl3 by R3, we get the line integral of B around the arbitrary closed path equal to mu naught I upon 2 pi into d theta 1 plus d theta 2 plus d theta 3 and so on. Since the sum of these small angles is 2 pi, hence the line integral of B around the closed path becomes mu naught I upon 2 pi into 2 pi or mu naught I. This is the proof of Ampere's circuital law in a general case. This result is independent of the size of the closed path, that is R. On the other hand, if the point P lies inside the current carrying conductor, which is at some distance from the axis of conductor, then according to Ampere's circuital law, line integral of magnetic field induction B around a closed path is equal to mu times the total current I threading the closed path, where mu is the permeability of the material of conductor. Ampere's circuital law is not new in content from Biot-Savart law. दोनों laws magnetic field ਅਤੇ current ਨੂੰ relate ਕਰਦੇ ਹਨ। दोनों ही steady electrical current ਦੀ same physical consequences express ਕਰਦੇ ਹਨ। Ampere's law ਅਤੇ Biot-Savart law ਦਾ relation ਬਿਲਕੁਲ Gauss law ਅਤੇ Coulomb's law ਦੇ relation ਦੀ ਤਰ੍ਹਾਂ ਹੈ। Both Ampere's and Gauss law relate a physical quantity on the boundary, that is magnetic or electric field, to another physical quantity, that is the source in the interior current or charge. Note ਕਰਨ ਵਾਲੀ ਗੱਲ ਇਹ ਹੈ ਕਿ Ampere's circuital law ਉਹਨਾਂ steady currents ਤੇ applicable ਹੈ ਜਿਹੜੇ time ਨਾਲ fluctuate ਨਹੀਂ ਕਰਦੇ। ਆਓ ਹੁਣ ਇਸ law ਨੂੰ ਇੱਕ straight long conductor ਅਤੇ cylindrical conductor ਵਿੱਚੋਂ current flow ਕਾਰਨ ਬਣੀ magnetic field ਦਾ expression obtain ਕਰਨ ਲਈ use ਕਰੀਏ। Magnetic field due to infinite long straight wire carrying current. Let us consider an infinite long straight wire carrying current I from X to Y. A magnetic field is produced which has the same magnitude at all points that are at the same distance from the wire. Let P be a point at a perpendicular distance R from the straight wire and B be the magnetic field at point P. It is well established that magnetic field B will be acting tangentially to the magnetic field line passing through P. Let us imagine a circular loop of radius r as an Amperian loop with center on wire such that point P lies on the loop. इस loop ते हर point ते magnetic field दा magnitude बराबर है। Point P ते magnetic field B circular loop दी circumference ते tangential है। जे Amperian path ਨੂੰ anti clockwise integrate ਕੀਤਾ ਜਾਵੇ ਤਾਂ B ਤੇ DL same direction ਵਿੱਚ act ਕਰਨਗੇ। Closed loop ਦੁਆਲੇ B ਦਾ line integral ਹੋਵੇਗਾ B DL cos 0 degree or B into integration of DL, which would be equal to B into 2 pi r. As per sign convention, here I is positive. By using Ampere's circuital law, we have line integral of B around the closed path equal to mu naught I. On equating these two relations, we get B is equal to mu naught I upon 2 pi r, or mu naught upon 4 pi into 2I upon r. This result for the infinite wire is interesting from several points of view. It implies that the field at every point on a circle of radius r with the wire along the axis is same in magnitude. In other words, the magnetic field is cylindrically symmetric. The field direction at any point on this circle is tangential to it. Thus, the lines of constant magnetic field form concentric circles. To verify this, let us see an activity.
ਜਦੋਂ ਇੱਕ ਲੰਬੀ ਸਟ੍ਰੇਟ ਵਾਇਰ ਵਿੱਚੋਂ ਕਰੰਟ ਲੰਘਾਇਆ ਜਾਂਦਾ ਹੈ ਤਾਂ ਵਾਇਰ ਦੇ ਆਸ-ਪਾਸ ਪਈਆਂ ਆਇਰਨ ਫਿਲਿੰਗਸ ਵਾਇਰ ਨੂੰ ਸੈਂਟਰ ਲੈ ਕੇ ਵਾਇਰ ਦੇ ਪਰਪੈਂਡੀਕੂਲਰ ਪਲੇਨ ਵਿੱਚ ਆਪਣੇ ਆਪ ਨੂੰ concentric circles ਵਿੱਚ ਅਰੇਂਜ ਕਰ ਲੈਂਦੀਆਂ ਹਨ. This shows that the magnetic field is associated with the current carrying wire. This is unlike the electrostatic field lines which originate from positive charges and end at negative charges.
The expression for the magnetic field of a straight wire provides a theoretical justification to Oersted's experiment. Another interesting point is that even though the wire is infinite, the field due to it at a non-zero distance is not infinite. Since B is inversely proportional to R, the magnitude of magnetic field increases as distance of point from the wire decreases. Can you suggest what would be the magnetic field at a point inside a conducting wire? Let us discuss it in a more general way. Let us consider an infinite long cylinder of radius r with axis xy and let current I be passing through the cylinder. A magnetic field will be set up due to the current I in the form of a circular magnetic lines of force with their centers on the axis of cylinder. These lines of force are perpendicular to the length of cylinder. First of all, we consider point P is outside the cylinder. Suppose R is the radius of Amperian loop. Here, R is greater than capital R. Let B be the magnetic field induction at P. It is acting tangential to the magnetic lines of forces at P. Here, B and dl are acting in the same direction. The line integral of B around the closed loop is equal to B dl cos 0 degree or B into the integration of dl, which would be equal to B into 2 pi r. According to Ampere's circuital law, line integral of B around the closed path is equal to mu naught I. On equating these two relations, we get B is equal to mu naught I upon 2 pi r. That is, B is inversely proportional to R. But if the point P is inside the cylinder, then R would be smaller than capital R. In this case, we may have two possibilities. Number one, if the current is only along the surface of cylinder, which is so if the conductor is a cylindrical sheet of metal, then current through the closed path is 0. Then according to Ampere's circuital law, B is also equal to 0. Second possibility is if the current is uniformly distributed throughout the cross section of the conductor. Then the current through closed path is given as I dash equal to I upon pi r square into pi small r square, which is equal to I small r square upon capital R square. Then line integral of B around the closed loop is equal to B into 2 pi r. Whereas, according to Ampere's circuital law, line integral of B around the closed path would be equal to mu I dash. On equating these two relations, we get B into 2 pi r equal to mu I into r square upon capital R square, or B equal to mu I small r upon 2 pi capital R square. In this case, B is directly proportional to small r. If we plot a graph between magnetic field induction B and distance from the axis of cylinder, it would be first increasing linearly up to capital R and then decreasing exponentially. Let us now use the concept of Ampere's circuital law to calculate the magnetic field produced by two commonly used and very useful magnetic systems, a solenoid and a toroid. Solenoid ਅਤੇ toroid equipment ਦੇ ਦੋ pieces ਹਨ ਜੋ ਕਿ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਪੈਦਾ ਕਰਦੇ ਹਨ। ਟੈਲੀਵਿਜ਼ਨ ਜ਼ਰੂਰਤ ਅਨੁਸਾਰ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਪੈਦਾ ਕਰਨ ਲਈ ਸੋਲੇਨੋਇਡ ਦਾ ਉਪਯੋਗ ਕਰਦਾ ਹੈ। ਸਿੰਕਰੋਟ੍ਰੋਨ ਹਾਈ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਪੈਦਾ ਕਰਨ ਲਈ ਦੋਹਾਂ ਦੇ ਕੰਬੀਨੇਸ਼ਨ ਦਾ ਪ੍ਰਯੋਗ ਕਰਦਾ ਹੈ। ਦੋਹਾਂ ਸੋਲੇਨੋਇਡ ਅਤੇ ਟੋਰੋਇਡ ਵਿੱਚ ਅਸੀਂ ਹਾਈ ਸਿਮੈਟਰੀ ਦੀ ਉਸ ਸਿਚੁਏਸ਼ਨ ਤੇ ਪਹੁੰਚ ਜਾਂਦੇ ਹਾਂ ਜਿੱਥੇ ਐਂਪੀਅਰਸ ਲਾਅ ਨੂੰ ਆਸਾਨੀ ਨਾਲ ਅਪਲਾਈ ਕੀਤਾ ਜਾ ਸਕਦਾ ਹੈ। First, we calculate the magnetic field due to a solenoid. A solenoid consists of an insulating long wire closely wound in the form of a helix. Here, we shall discuss a long solenoid, that is, whose length is larger as compared to its diameter. It consists of a long wire wound in the form of a helix, where the neighboring turns are closely spaced. So, each turn can be regarded as a circular loop.
ਆਓ ਸਰਕੂਲਰ ਕ੍ਰਾਸ ਸੈਕਸ਼ਨ ਦੀ ਇੱਕ ਲੌਂਗ ਸਟ੍ਰੇਟ ਸੋਲੀਨਾਇਡ ਲਈਏ ਜਿਸ ਦੇ ਕੋਈ ਵੀ ਟਰਨਸ ਇੱਕ ਦੂਜੇ ਤੋਂ ਇਨਸੂਲੇਟਿਡ ਹੋਣ। ਸੋਲੀਨਾਇਡ ਵਿੱਚੋਂ ਕਰੰਟ ਪਾਸ ਕਰਨ ਤੇ ਇਸ ਦੀ ਹਰੇਕ ਟਰਨ ਨੂੰ ਇੱਕ ਕਰੰਟ ਕੈਰਿੰਗ ਸਰਕੂਲਰ ਲੂਪ ਦੀ ਤਰ੍ਹਾਂ ਸਮਝਿਆ ਜਾ ਸਕਦਾ ਹੈ ਜੋ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਵੀ ਪੈਦਾ ਕਰਦੀ ਹੈ। ਸੋਲੀਨਾਇਡ ਦੀ ਟੋਟਲ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਇਸ ਦੇ ਸਾਰੇ ਟਰਨਸ ਕਾਰਨ ਪੈਦਾ ਹੋਈ ਮੈਗਨੈਟਿਕ ਫੀਲਡਸ ਦਾ ਵੈਕਟਰ ਸਮ ਹੈ। ਇਸ ਸੋਲੀਨਾਇਡ ਦੇ ਬਾਹਰ ਕਿਸੇ ਪੁਆਇੰਟ ਤੇ ਨੇਬਰਿੰਗ ਲੂਪਸ ਕਾਰਨ ਮੈਗਨੈਟਿਕ ਫੀਲਡਸ ਇੱਕ ਦੂਜੇ ਨੂੰ ਅਪੋਜ਼ ਕਰਦੀਆਂ ਹਨ। ਸੋਲੀਨਾਇਡ ਦੇ ਅੰਦਰ ਕਿਸੇ ਵੀ ਪੁਆਇੰਟ ਤੇ ਮੈਗਨੈਟਿਕ ਫੀਲਡਸ ਸੇਮ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਹੁੰਦੀਆਂ ਹਨ। ਨਤੀਜਨ ਸੋਲੀਨਾਇਡ ਦੇ ਬਾਹਰ ਇਫੈਕਟਿਵ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਵੀਕ ਹੋ ਜਾਂਦੀ ਹੈ ਜਦੋਂ ਕਿ ਸੋਲੀਨਾਇਡ ਦੇ ਅੰਦਰ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਸਟਰੋਂਗ ਅਤੇ ਯੂਨੀਫਾਰਮ ਹੁੰਦੀ ਹੈ ਜਿਹੜੀ ਸੋਲੀਨਾਇਡ ਦੇ ਐਕਸਿਸ ਦੇ ਡਾਇਰੈਕਸ਼ਨ ਵਿੱਚ ਐਕਟ ਕਰਦੀ ਹੈ। ਜਦੋਂ ਸੋਲੀਨਾਇਡ ਨੂੰ ਜ਼ਿਆਦਾ ਤੋਂ ਜ਼ਿਆਦਾ ਟਾਈਟਲੀ ਪੈਕ ਕੀਤਾ ਜਾਂਦਾ ਹੈ ਤਾਂ ਸੋਲੀਨਾਇਡ ਵਿੱਚੋਂ ਕਰੰਟ ਲੰਘਣ ਕਾਰਨ ਸੋਲੀਨਾਇਡ ਦੇ ਬਾਹਰ ਇਸ ਦੇ ਸੈਂਟਰ ਦੇ ਨੇੜੇ ਇੱਕ ਪੁਆਇੰਟ ਤੇ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਜ਼ੀਰੋ ਹੋ ਜਾਂਦੀ ਹੈ ਅਤੇ ਸੋਲੀਨਾਇਡ ਦੇ ਅੰਦਰ ਕਿਸੇ ਵੀ ਪੁਆਇੰਟ ਤੇ ਇਹ ਸਟਰੋਂਗ ਅਤੇ ਯੂਨੀਫਾਰਮ ਹੁੰਦੀ ਹੈ।
Let us now calculate the magnetic field induction due to the solenoid. Let n be the number of turns per unit length of the solenoid and I be the current flowing through the solenoid and the turns of the solenoid be closely packed. Imagine a rectangular Amperian loop PQRS near the middle of the solenoid where PQ is equal to L. Let the magnetic field along the path PQ be B and 0 along RS. As the paths QR and SP are perpendicular to the axis of solenoid, the magnetic field component along these paths is also 0. Therefore, the paths QR and SP will not contribute to the line integral of magnetic field B. The total number of turns in length L is equal to N into L. The line integral of magnetic field induction B over the closed path PQRS is equal to the line integral of magnetic field induction B over PQ plus line integral of magnetic field induction B over QR plus line integral of magnetic field induction B over RS plus line integral of magnetic field induction B over SP. Here, line integral of B over PQ is equal to BL, whereas over QR, over SP and over RS, it is 0. Therefore, the line integral of magnetic field induction B over PQRS is equal to BL. However, according to Ampere's circuital law, it should be equal to mu naught times the total current through PQRS, that is, mu naught into number of turns in rectangle into current I, that is, mu naught N L into I. This gives BL equal to mu naught into NLI. Therefore, B is equal to mu naught Ni. This gives the magnetic field induction at a point well inside the solenoid. However, at a point near the end of a solenoid, the magnetic field induction is found to be mu naught Ni by 2.
ਕਰੰਟ ਕੈਰਿੰਗ ਸਟ੍ਰੇਟ ਸੋਲੇਨੋਇਡ ਦੀ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਲਾਈਨਸ ਦੀ ਸਟੱਡੀ ਕਰਨ ਤੇ ਇਹ ਨੋਟਿਸ ਕੀਤਾ ਗਿਆ ਕਿ ਇਹ ਵੀ ਪਰਮਾਨੈਂਟ ਮੈਗਨੇਟ ਦੀ ਤਰ੍ਹਾਂ ਹੀ ਮੈਗਨੈਟਿਕ ਫੀਲਡ ਪ੍ਰੋਡਿਊਸ ਕਰਦਾ ਹੈ। ਸੋਲੇਨੋਇਡ ਦੇ ਜਿਸ ਸਿਰੇ ਤੇ ਕਰੰਟ ਐਂਟੀ ਕਲੌਕਵਾਈਜ਼ ਹੈ ਉਹ ਨਾਰਥ ਪੋਲ ਦੀ ਤਰ੍ਹਾਂ ਕੰਮ ਕਰਦਾ ਹੈ, ਜਦੋਂ ਕਿ ਦੂਸਰਾ ਸਿਰਾ ਜਿੱਥੇ ਕਰੰਟ ਕਲੌਕਵਾਈਜ਼ ਹੈ ਉਹ ਸਾਊਥ ਪੋਲ ਦੀ ਤਰ੍ਹਾਂ ਕੰਮ ਕਰਦਾ ਹੈ।
Toroid is a hollow circular ring on which a large number of turns of a wire are closely wound. In fact, a toroid is an endless solenoid in the form of a ring. An ideal toroid has a circular and closely wound coil turns. We will now calculate the magnetic field induction due to an ideal toroid. Let N be the number of turns per unit length of toroid and I be the current flowing through it. A magnetic field of constant magnitude is set up inside the turns of toroid in the form of concentric circular magnetic field lines. We know that the direction of the magnetic field at a point is given by the tangent to the magnetic field line at that point. Let us draw 3 circular Amperian loops 1, 2 and 3 of radii R1, R2 and R3 to be traversed in clockwise direction in such a way that the points P, S and Q may lie on them. However, the circular area bounded by loops 2 and 3 both cut the toroid. Each turn of current carrying wire is cut once by the loop 2 and twice by the loop 3. Let B1 be the magnetic field along loop 1. Hence, line integral of magnetic field B1 along the loop 1 is equal to B1 into 2 pi R1. Since loop 1 encloses no current, according to Ampere's circuital law, line integral of magnetic field B1 along the loop 1 is equal to mu naught times 0. Therefore, B1 is 0. Let B3 be the magnetic field along the loop 3. The line integral of magnetic field B3 along the loop 3 is equal to B3 into 2 pi R3. From the sectional cut, it can be noticed that the current coming out is cancelled exactly by the current going in. Therefore, the total current enclosed by loop 3 is 0. Hence, according to Ampere's circuital law, line integral of magnetic field B3 along the loop 3 is also equal to 0, or B3 is equal to 0. Let B be the magnitude of magnetic field along the loop 2. The line integral of magnetic field B along the loop 2 is equal to B into 2 pi R2. Since the current enclosed by the loop 2 is equal to the number of turns into current in each turn, that is 2 pi R2 N into I. Hence, according to Ampere's circuital law, integral of magnetic field B along the loop 2 is equal to mu naught times total current, that is mu naught into 2 pi R2 Ni, or B into 2 pi R2 is equal to mu naught into 2 pi R2 Ni. This gives B equal to mu naught times Ni. Here, it can be noticed that this result is similar to that of a solenoid. With this, we come to the end of today's lesson. Let us quickly summarize what we have done so far. According to Ampere's circuital law, the line integral of magnetic field induction B around a closed path in vacuum is equal to mu naught times the total current I threading the closed path. Ampere's circuital law holds good for steady currents which do not fluctuate with time. Magnetic field induction B due to a long straight current carrying conductor is equal to mu naught I upon 2 pi R. It is found that for a long wire, magnetic field is cylindrically symmetric. A solenoid consists of an insulating long wire closely wound in the form of a helix, and toroid is a hollow circular ring on which a large number of turns of wire are closely wound. However, a toroid is an endless solenoid in the form of a ring. In terms of magnetic field induction, for a tightly packed long solenoid or a toroid, it is 0 outside the solenoid or toroid, but inside a long solenoid or a toroid, B is equal to mu naught times Ni, where N is the number of turns per unit length. I believe that all of you have now understood the concept of Ampere's circuital law and its applications. Let me ask you some questions now. My first question is, what is Ampere's circuital law? The answer is, according to Ampere's circuital law, the line integral of magnetic field induction B around a closed path in vacuum is equal to mu naught times the total current I threading the closed path. The next question is, what is the expression for the magnetic field induction due to a current carrying cylindrical conductor? The answer is, magnetic field B outside the cylinder is equal to mu naught I upon 2 pi R. On the other hand, inside the cylinder, it is equal to mu I R upon 2 pi capital R square. I hope you have enjoyed the lesson. Thank you for paying attention to today's class. See you in the next class again.